Hey, welcome back everyone. So my name is Zach Vines, and what we're going to go over today is one of the more introductory concepts in statistics. It's probably one of the first things that you learn about when you first enter your introductory statistics course. So we're just going to be talking about probabilities, and we're going to segue that into independent events and mutually exclusive events, kind of give you the formulas that back those up, how you can solve problems with them, and kind of wrap everything up with a nice example. But to start with, I just want to introduce the general concept of probability, which is pretty simple, and you'll see once we talk about this example right here. So the way I think about probability, it's not the technical definition of it, but I just think about it like the part we're interested in out of the whole. So I think that's better demonstrated with an example. So let's just say we have 100 people in a room, okay? And we know that 70 of those people are going to be males and 30 of those people are going to be females. So if I go into that room and I pull a random person out of there, I'm wondering what is the probability that the person I pull out of that room is going to be a male? Well, the part I'm interested in are the number of males. Like male is the specific category that I'm targeting right now. So I'm going to start with the number of males as the part I'm interested in, which we have 70 because we were given that information, out of the whole, which is just 100 people in the room as a whole. So 70 divided by 100 is 0.7 or 70%. It's as simple as that. Same deal goes with the females. If I know that there's 30 females in the room, and that's the part that I'm targeting at that point in time, the part I'm interested in is the number of females, which is 30, out of the whole, which is 100, equaling 0.3 or 30%. So you can see that these two categories, the male and females, they're complements of one another because those are the only two categories that we have in question in this situation. Out of that room, there are either males or females. And so when you add them all together, it ends up being 100% of the possibilities in question. So even if I didn't know the females, like the number of females in the room, knowing that those are the only two combinations possible and that 70% of the people in that room are males, I would have to think then that the other 30% equaling that 100% would be the number of females. So that's just the basic introduction of the probability, just the concept of it. But now just getting into the variables that we're going to use in these formulas that we'll show in just a second. When we say P of A, P of B, et cetera, those are just the probabilities of certain events. So this is just the probability of event A. And you can call an event by, a letter like that, just say this is A, this is B, or you can say, the probability of being a male we'll use as M, which makes perfect sense that we would do that, F with the female, so on and so forth. So those are just the basic probabilities there. Whenever we're dealing with kind of combined probabilities where we have P of A in this little upside down U right here, B, that means and. So that's the probability of both A and B happening at the same time. So the memory tool I use to remember what this variable means right here is that I think about this upside down U as a lowercase n, and it almost looks like it's about to spell and. So I think about the n right here, it's an upside down U, but I think about that as the n and to remember it like that. And then this right here, just flip it upside down, is the probability of A or B happening. So it's the probability that at least one of those two is going to happen. Not necessarily at the same time, could be, but it's just one or the other happening. And then we have probability of A given B right here. So this line right here represents given. So what that means is that we are locking in the fact that B has already occurred. And we're asking ourselves, okay, given that B is locked in and that it's definitely already happened, what is the probability of A? So each of these kind of have their own formulas, but the formula you use for each of them kind of depends on what category it falls into, whether or not it's independent, if it's mutually exclusive. So let's get into those definitions, those formulas right now. Okay, so now we're going to talk about what it means for something to be mutually exclusive and what it means for something to be independent. We're going to segue that into the formulas for P of A or B, A and B, et cetera, based on those categories. And you're going to see that if you can kind of take the category it falls into, whether or not it's mutually exclusive or independent, and then think about what the formula would be based off of that, everything becomes a lot more clear, especially as you're working through some of these problems. So for two events to be mutually exclusive, that means that they cannot occur at the same time. So basically, the example I like to use for it is I flip a coin, and it's going to land on either heads or tails. If I flip a coin, there's no chance that it's going to land on both heads and tails at the same time. That's just impossible for that to happen. So in that case, those two events would be mutually exclusive. And likewise, for something to be independent, that means that one event occurring doesn't impact the likelihood of another event occurring. So you can come up with pretty much any example for that. One that I just think of offhand is that if I don't know, take a shower this morning, what's the chance I take a shower this morning versus the chance that I spend 20 minutes in the car driving to school or work that day? they don't affect one another at all, right? But one thing to keep in mind is that if two events are independent, that means that they are not mutually exclusive. So let's think about that just based on the definitions to start with. If we're told up front that they are independent, meaning that we have event A and event B, and when event A happens, that has no impact on the probability of event B happening. So lock that in for just a second. And then we'll think about when something's mutually exclusive. It means that two events cannot occur at the same time. Well, if two events can't occur at the same time, that means that if one happens, the other one can't happen, right? That sounds like a pretty dependent relationship on one another, right? So if it's independent, that means that they're not mutually exclusive. It's not necessarily the other way around, though. So that's kind of a tricky thing, especially as we begin to work through a few problems, is that unless you are told that two events are independent, don't assume they're independent and just start plugging into these independent formulas. You need to kind of base it off of what you have given and what you can gather as far as what category it might fall into, like it being mutually exclusive or not mutually exclusive and things like that. And don't assume independence from the get-go just because you have the formulas and could plug that in, because if it's not independent, these formulas do not apply. So let's go ahead and kind of start talking about those formulas. So mutually exclusive, these are the formulas for A or B, A and B, and A given B. And these actually make perfect sense because, again, think about what mutually exclusive means and then translate that to the formulas right here. So let's talk about the probability of A and B to start with. So if we are already understanding that these two events are mutually exclusive, they cannot occur at the same time. The probability of A and B, meaning that those two things happen at the same time, that would just be 0. If they can't occur at the same time, there's a 0% chance that A and B happens at the same time. So that makes perfect sense. If the probability of A given B, that equals 0 as well, because if B has already happened, we're locking in the fact that it's a given that B has happened. A cannot happen if, by definition, they're mutually exclusive. So that's going to be 0 as well. So finally, if there are two events that cannot occur at the same time, we're wondering what's the probability that one happens or the other one happens, those are just standalone probabilities that if you add them together, that is the probability that one event happens or the other event happens. So I don't have it written down now. I will in just a moment of formulas when they're not mutually exclusive. It gets a little bit trickier and we'll have to do some algebra to maybe rearrange some of the formulas, find exactly what the question might be asking us for, do an example to kind of correlate with that. But the mutually exclusive formulas make the most intuitive sense, I would say, from the get-go. As far as the independent formulas go, these are mostly just things to remember where we have, probability of A and B is just the probability of A times the probability of B. So if you already know that they're independent, and you have to know that before you just jump into this formula, have some sort of information to indicate that, then you can use this formula right here, just multiply those two together. That's the probability that both of them happen at the same time. Now the probability of A given B when they're independent, and you know that, is actually just going to be the probability of A. But that makes intuitive sense as well, because we're saying that the likelihood of one event happening, like one event happens, that doesn't impact the likelihood of the other event happening. So A, given that B has already happened, well, if B's already happened, that doesn't affect the probability of A happening. A is just going to happen based on its own probability from the beginning. So it's just going to be its own standalone probability in the first place. Same deal when we have probability of B given A. It's just going to be the probability of B, because just because A happened, that doesn't affect whether or not B is going to happen. It's just its own standalone probability from the get-go. So that's as far as the definitions of mutually exclusive and independent, the formulas for each of those two. So I'd recommend writing those down because you're going to need them for the problem towards the end. But now we'll get into the formulas for whenever they're not mutually exclusive. Okay, so now here are the formulas whenever we know that two events are not mutually exclusive. Okay, so this means that those two events could happen at the same time, because mutually exclusive means that they cannot, so the opposite would be what's going on in this case. And so the formulas that we have right here is just that P of A given B, so if you're looking for that, it would simply be P of A and B divided by P of B, okay? And I'll kind of show you what we're doing right here in just a moment, but to go ahead and wrap this part up, if you're looking for P of A or B, you would just take your P of A plus your P of B and subtract the probability, the P of A and B happening at the same time. So something I want to point out is that when we're first getting into these problems and we have a lot of questions that'll ask us, not necessarily for P of A given B or P of A or B, we might know that these events are not mutually exclusive, and yet we'll be asked for something like P of A and B, and we go, we don't have a formula for that. What are we supposed to do? All we have is P of A given B and P of A or B. Well, you just simply manipulate the formula, and one little trick that I like to show students whenever we're just dealing with a simple, something like this, x equals y divided by c, just a number equals a number divided by another number. So x equals y divided by z right here. I always just like to put it into the form of a triangle, and you'll see kind of how that loops around right here, how we manipulated this formula. So just to kind of show this example, x equals y divided by z. There's just random numbers, let's say. Why? Because this is in the numerator right here. It's on the top. Let's draw out a triangle and put what's on the top right here as the top of the triangle, okay? And if that's the case, what's on the left side right here, we're going to put on the bottom left of the triangle, and what's on the right side right here, the z, we're going to put on the bottom right of the triangle, okay? So let's say I'm looking for x, so we're solving for x right here. You can see that if I don't have x, and that's what I'm looking for right there, what I'm left with, and let's say I do know what y and z are, is simply y divided by z, and it's divided by because the y is on top of the z. So that's pretty simple because we already have the formula for it, but let's say that we were looking for z. So I don't have z right here, so pretend that's not there at all, but I know what y is and I know what x is. Well, to find z, all I have is what's on the top, that y, divided by x, what's on the bottom. So z would equal y divided by x. And finally, if you're looking for y right here, what's in the numerator, because x and z are right next to each other, and that's all you have, do x times z, and that's going to give you y. So the reason I bring that up is because right here, you can manipulate this equation however you need to, as long as you do it properly, to find any one of these characteristics, assuming you have the other two. So for instance, if I'm looking for P of A and B, and I'm given P of A given B and P of B, well, this little thing right here, the P of A and B, would be like my y. So I'm going to treat that like the top of the triangle, and I'm going to say that what's left are just the two bottom parts of the triangle. So multiply these two things together, and so it's P of A given B times P of B, and that's going to give you P of A and B right there. So one last thing to kind of talk about that is that the P of A and B formula, given the not mutually exclusive designation, it also works if they ask you for, let's say, P of B given A. So this only covers A given B, but the way you can translate this formula into the B given A is by simply flipping the B and A right here. So we start with A given B, simply turn that into B given A, but instead of multiplying by P of B, multiply by P of A instead. So it's pretty much just turning the B's into A's on the right side of the equation, and that will also be true. It just depends on whatever problem you're given, whatever you're looking for. So with that, let's go ahead and get into one more problem to kind of wrap everything up. Okay, so now we're dealing with this example right here where we are given P of A, P of B, P of A given B, and we are asked what is P of A and B, and then we're asked whether or not A and B are independent. So we're just going to kind of go in order here. So to start with, remember, we had a lot of different formulas as far as what P of A and B was. We had the one where if they were mutually exclusive, it would just simply be 0 because those two events can't happen at the same time if we already know that it's mutually exclusive. We also have, if they're independent, we should be able to take just P of A times P of B and get our P of A and B. But since we're not directly told that it's independent, remember, never assume that if you're not already given that information or have something that you can use to check to make sure of that. So at this point, we go, okay, we have P of A, we have P of B, we have P of A given B. So what formulas did we have from everything we just went over that includes all of that except for P of A and B, kind of like let that be the missing variable? Well, what we just went over before was that we had our P of A given B formula right over there equals P of A and B divided by P of B. So again, it's not the direct P of A and B formula, but all you have to do is manipulate that equation, and at that point we have the P of A given B, we have the P of B, so the only thing that's left is what we're looking for, so that's what we're going to use to solve it. If we know that all of these pieces of information are true, then if we plug that into that equation, the last remaining component should give us the right answer. So let's see if that works out. So we have P of A given B equals P of A and B divided by P of B. Well, if I'm wanting to solve for, let's say that's the top of the triangle, remember, then I'm just going to multiply P of A given B by P of B to get my answer. So at that point, I'm just going to do our 0.5, which is our P of A given B right here. I'm going to multiply it by our P of B, which is our 0.25. And when we do that, our answer ends up being 0.125. That's going to be our P of A and B right there. So one thing we can check to make sure that it was a good thing we didn't just do P of A times P of B, which was that independent formula, is we're asked, are A and B independent? Okay, well, we had all those formulas that were listed under the independent category, right? So if I'm able to plug in P of A times P of B, because under the independent category, P of A times P of B equals P of A and B. If I can plug in just P of A times P of B and it gives me this P of A and B that I just found, I know they're independent because when I plug it into the independent formula, it checks out perfectly. If it's not, I know that they're not independent, and it was actually a good thing I didn't just go straight into P of A times P of B. So when we do that, we just take P of A times B of B, and sure enough, that's not 0.125 at all. So we know that the answer is that they're not independent. So just kind of as an overview, it's really important to think of the definitions of mutually exclusive and independent before you just jump right into the formulas. Those are designations that you may have information to kind of indicate whether or not they're mutually exclusive, whether or not they're independent, but you don't know for sure until you kind of look at the other information. So one more thing I want to point out is that when we did P of A given B, we jumped into the not mutually exclusive category. The reason I knew that was the case was because if P of A given B is 0.5, that can't be mutually exclusive, because under the mutually exclusive category, we had that if they're mutually exclusive, P of A given B is actually going to be 0. In this case, that's not 0, so we know it can't be mutually exclusive. So we can use the information like that to sort of gather more pieces of information to find what category it falls into. Never take the fact that it's mutually exclusive or independent unless you're told that or have some information to indicate otherwise. Hold on to those definitions, plug them into the formulas, remember your triangle rule, and you'll be able to do these problems like clockwork. So I hope that helped out.